Swayam Prabha. Digital India. Educated India.
Okay, good morning everyone and welcome to this second day of this GIAN course on modeling and simulation of granular systems. So, as discussed in yesterday's class, what I am going to today is to give you an introduction to the discrete element method, the numerical method called discrete element method, which is typically used for simulating granular systems. So, what are the issues therein and how do we go about simulating motion of granular systems and what are the equations that we are solving in this process. So, before we talk about anything about the discrete element method, which is a numerical method, is used to model a physical system, right, in order to understand what is the behavior of the system. So, even before we actually talk about understanding the behavior by developing a mathematical model and so on, this is a statement that is an important statement to be remembered by everyone who does numerical computation. By definition, all models are wrong because they will not be able to represent the actual physical system accurately, right. There is some level of assumption that is involved, although they are wrong in the sense that they cannot represent the physical system completely, but they are useful. Some of them are useful and hence we still do numerical computation. So, whenever we are doing numerical computations and analyzing the results, we have to take these results with a pinch of salt because there are several assumptions involved and we do not really know what is the effect of this assumption unless we corroborate our results with the experiments. Why we need to study granular materials and discrete element method, we have done that yesterday. So, we have seen the applications of granular materials in industries like mining industry, food, pharma, energy, manufacturing, advanced additive manufacturing techniques and even movies, right. You actually have so many Hollywood movies nowadays which sort of simulate, but it looks like it is, although it is probably an animation, but there seems to be some physics respected by the model that we are seeing here. So, we can make physically realistic we can develop physically realistic animations if we are able to make these computations more efficient. Okay. Okay, so these are all the industries where you have granular materials playing their role. In fact, every industry that you can name of will have some granular material playing their role. So, what are the problem areas that we are concerned with? So, this is one example that we have seen, collapse of silos, the storage of food grains and so on, and the integrity of the silo is an important design problem. Landslides, for geotechnical engineers, one needs to understand how the landslide take place in order to minimize the loss to the human life as well as property. Excavations, how do you design the machinery in order to improve the efficiency of excavation, and rover motion. So, these are all the problem areas that are of interest. I am only shown a couple of them, but there are numerous problems that require our intervention to understand the physical behavior of the granular systems. So, what we have seen in yesterday's lectures, what Professor Jidong Yao has shown and I have shown, what we probably are convinced by today is that granular materials ubiquitous, they are everywhere. There is, you see around, you find granular materials, you just need to look at them with the right perspective. So, the question is then why not study them, because they are useful, right, they help us solve several problems. So, as I discussed yesterday, the DEM, the discrete element method, is one of the popular techniques to simulate the behavior of granular material. So, what is DEM? It is simply a numerical modeling or a computer simulation approach to study the motion of granular materials or study the motion of collection of particles. That is what a DEM, that is what DEM means. It is simply a numerical technique. And what it does is, it explicitly considers the individual particles and their interactions. So, most of the continuum approaches do not consider the individual interactions and then attachment and detachment of contact and so on. Discrete element method by nature, it allows us to consider the interaction between the particles, which may or may not be in interaction all the time. So, that interaction may, at some point of time there may be interaction between two particles, at some other point of time the interaction may not exist. That means, the contacts establishment and detachment happens all the while during the simulation. So, this is handled by discrete element method very efficiently. So, it is an alternative to typical continuum approach that we are all familiar with for granular materials. So, wherein you do not really have access to what is happening at each and every particle level. So, what is the beauty of this system is that we said there is the method considers the interaction between the particles, right, and the method allows us to decipher extremely complex macroscopic response by employing very simple contact interaction models. You really do not need to have a very complex contact interaction model. What do I mean by that? When two particles are touching each other, what is the force that is generated? Is it linear or non-linear? Is there some cohesion? So, you actually need not have extremely complex model of interaction between contact interaction between the particles. With very simple models, you can actually get rich information about the complex macroscopic phenomena. So, that is one of the USPs of this method. Okay. So, why we use DEM instead of continuum? As I already said, continuum simulations require, if you have to talk about granular materials, because they are as we have discussed, they behave sometimes like solids, sometimes liquids, and they change their phase every now and then whenever the right condition arises, right. And hence, to describe such a behavior through a single continuum constitutive behavior is very complex. And even with simple contact relations, DEM can bring out complex continuum response, meaning you do not really need to have very sophisticated contact relation. Even with simple contact relation, you will see the rich continuum response information from the DEM simulation. The another important aspect or the main difference between a DEM simulation and a continuum simulation is that through DEM simulations we can get access to the microscopic interactions. When I say microscopic interaction, I am actually talking about what is happening at the particle level, individual particle level. Although as an engineer you are interested in the macroscopic behavior of a granular system, but still the macroscopic behavior of that granular system depends on what is happening at the micro scale, that means at the particle scale, and that is something that we can naturally get through this method. And not only that, when you are dealing with complex particulate systems or granular systems, sometimes we do not know what is the right constitutive behavior to be used when they are to be simulated as continuum materials, because the DEM method, we will see DEM as a method is computationally very expensive. So, sometimes you might want to simulate your system using continuum approach, because you are not interested in what is happening at the microscopic level. So, that means you might want to use the methods like finite element method. But then it is, although the constituent particles are say linear elastic in nature, but the macroscopic response will not be linear elastic. It will be some complex nonlinear response. So, what will be the constitutive response of such a granular assembly is something that we can deduce from DEM. So, you can actually do a laboratory surrogate experiment using DEM and then deduce the macroscopic constitutive relation that can be simply plugged into your finite element model. Yeah. So, when you talk about understanding, so I hope you are familiar with finite element method. Okay, even if you are not familiar with finite element method, let us say if you are subjecting a body to an external force, right? You take, let us take the simple case of a bar which is subjected to an axial load. Oops. Okay, an axial load P and whose cross sectional area is A, length is L. And now let us say this is a material having an elastic modulus E. So, that means let us say this is an aluminum bar. Okay. Now, you take exactly the same dimensions, same geometry, everything, load is also same, A and L are same, but now it is not aluminum, let us say it is a steel bar. So, the differentiating factor between the bar being aluminum or steel is its elastic modulus. Now, if you calculate the displacement in this rod is delta equal to P L by AE aluminum, that is in the aluminum bar, delta A delta steel is equal to P L by AE steel, right. So, depending upon what this material is, your deflection will be different or your deformation will be different. So, what is the constitutive relation? This here the constitutive relation relates. So, for example, if you say delta by L is what? That is strain, that is equal to P by A times E, and P by A is your stress. So, sigma by E. So, sigma is equal to E times epsilon, right. How your strain or a kinematic quantity is related to your stress is connected through this elastic modulus E. As long as the material is linear elastic, you will have a single elastic modulus. So, for example, if you do the stress strain, plot the stress strain response of any material, it looks something like that, right. For example, it is a linear elastic material and then it becomes non-linearly elastic. Let us say you are only interested in the linear elastic regime. Okay. Then the relation between say stress and strain is given by a single slope because it is linear. But what happens in granular materials is this part, if you would plot this stress strain response for a collection of particles made of steel which is also linear elastic, then none of the particles are undergoing plastic deformation, and now if you compress this fellow and if you plot stress strain response, you will see something like that. You will see a non-linear elastic response, right. So, here your constitutive relation, not contact constitutive relation, here I am talking about a constitutive relation as if this is a continuum. So, now it is behaving like a non-linear elastic material whose stiffness is changing as a function of strain. Now, I cannot represent that as sigma is equal to E times epsilon, but I have to represent this E as a function of epsilon times epsilon, because E depends on what is my epsilon. So, that is what we call a constitutive relation. Now, depending upon what my internal material is, this response is going to be different, right. I will be able to find out by doing DEM simulations what this what this macroscopic constitutive relation is. That means, basically connecting strain and stress. Okay. If you have it is primarily because of the interactions. What is the way that you are seeing the stress in your stress strain response is coming because of several factors that are there in the system. For example, the friction between the particles plays a role, right, and the friction between the particles that are in contact. While you are compressing, not all the particles are in contact, some particles may not be in contact, right. So, the number of particles that are establishing contact and the amount of contact area will be changing as a function of load, and hence it is not the same material every time you are compressing. Every time instance you are actually going from one material to another material, if you look at as a macroscopic sense. That is the reason why it cannot be, it will not in general have a same slope, it will change its slope, and that is what we perceive as a nonlinear response. Okay. All right. So, what is the motivation for using DEM? Yes, it can replicate an experiment, and what you can do is you can apply, so the experiment through in which we can apply loads and displacement to a virtual model. It allows us to simulate a physical laboratory experiment, and it allows us to monitor closely what is happening to the particle contact, particle orientation, contact forces, etc., which are otherwise not accessible. What do we mean by that? If you take a container of cereals and you are applying force, will you be able to, by doing, when you are applying the load, what is that you are measuring? Force displacement. What is the force displacement that you are measuring? You are only measuring the macroscopic force displacement. Are we able to see what is happening to the deformation of each and every particle? We are not able to see that. It is extremely difficult. You can possibly use some sophisticated imaging techniques to see what is happening to each and every particle, but that is way too expensive, right. So, by using discrete element method, because it is a numerical technique, although you are compressing, you measure the macroscopic response, but you are also having access to what is happening at the particle level. So, that is one of the USPs of the method. As I said, it is impossible to access such information in an experiment, and DEM models, so which basically means it allows us to look inside the material. When I say inside the material, inside a granular system, you can actually sit on one of the particles and see what is happening, right. That is the meaning of running a granular material simulation. And the second motivation is it allows us for analysis of mechanisms in large displacement problems like geomechanics, for example, landslides if you want to simulate, right. So, you will be able to understand the mechanism. So, why at a particular instance the stability of the system is gone and hence suddenly a large chunk of mass is moving, and what are the conditions that make this possible, right. So, can we, suppose if you are doing some construction on a slopy terrain, so what are the considerations that we need to take in order to ensure the stability of the soil in that region is such that your building does not collapse, right. And it also allows us to model various mechanisms such as internal erosion, scour and sand production in oil reservoirs, clogging in granular flows. When does a granular flow clog? When does a particle flow in a chute stop? And what happens to particle wall interactions? If you have a fluid, what happens to the fluid particle interactions? All these things can be accessed. So, yes, I have said nice things about the method. So, what are the strengths? It gives, most important strength is it gives us grain scale interaction, meaning it allows us to look at what is happening at each and every particle. And the algorithms that we are using to simulate the motion are explicit in nature, and hence the convergence is not an issue. Explicit algorithms, you ensure that your time step is small, I will talk about it, and hence you need not worry about the convergence of the problem. Although there is an issue if you do not use the right time step, you might actually be getting a wrong answer. You need to ensure that you have a sufficiently small time step. Okay? And it can capture the complex behavior through physical processes that happen at the grain scale. It allows us to do a virtual experiment. So, suppose if you are doing a triaxial test in a lab, right, the same thing can be done using in a DEM simulation setup, and then see whether we are able to compare our results with the experimental data or not. So, you can do a virtual experiment. And one of the striking features with the development of DEM over the years is that it can now be combined with other numerical techniques in order to enhance its capabilities. For example, you can now combine CFD with CFD and DEM, so that you can study particle fluid interaction and what happens when a particle laden flow takes place, how particles influence the fluid field and how fluid field influences the particle. Similarly, you can do FEM DEM, coupling FEM DEM. For example, if you want to study how, suppose you are doing excavation, right, and how the bucket erosion takes place, how the bucket's wear and tear takes place as a function of interaction between the particles. That is something that you can do by coupling FEM and DEM. There are several other applications that you will come across which use the strong coupling between these kind of methods. However, although it is very, it shows a lot of promise, it also has limitations. It is computationally very expensive, right. So, as you increase the number of particles, your computational time does not increase linearly, it increases non-linearly. So, the computational cost is one of the reasons why you might not want to simulate everything you at the keeping particle level, because although the method itself is very simple, but the cost is so high that you may have to avoid using the method when it is not meaningful to use the method. And contact constitutive response, for example, you are talking about particle interactions, right, particle-particle interactions. These particle-particle interactions, we do not know what this particle-particle interaction is. So, now the question is, how do we get this particle-particle interaction? Suppose if steel and steel are interacting, steel and copper are interacting, steel and thermocol are interacting, how would you write contact constitutive relation? What do I mean by that? When I say contact constitutive relation, it is basically some sort of force displacement response, how the force and interpenetration are related. Like force and displacement are related through stiffness of a spring, where stiffness is the constitutive property. Similarly, when two particles are interacting, depending on the type of the particle and the extent of deformation that they are subjected to, what is the contact constitutive response? This is something that we need to get through experiments, because there will not be these contact constitutive relations will not be available right away, but you have to do some experiments, and once you have certain models which can reasonably well represent the contact constitutive response, we can use those models, right. We will talk about one or two of such models. And another issue is a large fraction of DEM simulations use spherical particles because they are easy to deal with. And today, as yesterday Professor Javo has shown us, that we can do all kinds of complex geometries, but they increase the computational cost significantly, right. So, you need to balance whether is it a good idea for me to go for such a complex geometry at the cost of high computational requirements, or should I just live with spherical particles. So, the spherical particles, so the generation of realistic particle beds, so particle shapes and particle beds is an issue. We may not be able to use exact particle shapes. If we want to use it, you have to spend a lot of time and money. Okay. So, what are the ingredients of DEM? Okay, you said this gives us particle level interactions. So, if it has to give particle level interactions, what are the inputs? What do we need in order to run this DEM simulations? There are physical inputs. You should know what is my particle shape, what is my particle size, particle density, and what is the contact radius. That is an indirect input. I will talk about it a little later. And then what is the wall elasticity? So, you have a rigid wall or an elastic wall. So, you have a particle system and you have a set of particles in the container, and the container wall, is it relatively rigid compared to the particles or compliant compared to the particles, right? Because that matters. That decides what is the macroscopic response, whether the particles are able to push the wall or wall is restraining the particle motion. They are two different things, right? And then you also have mechanical parameters, which is basically contact stiffness. This is what I mean by contact constitutive relation, how the normal interaction, if you have two particles, right, how the normal interaction between the particle is taking place, how the tangential interaction is taking place, right. So, you basically are talking about introducing a normal spring and a tangential spring, shear spring. What is the stiffness of this normal and shear springs, and is there some dissipation that is to be incorporated in the model, because there is always friction between the particles. How will you account for frictional dissipation, right? That is coefficient of friction is another parameter, and the contact adhesion. What do we mean by contact adhesion? If you have two particles, if they are bonded, for example, and if you are trying to separate these two particles, will they immediately separate or they will offer some resistance if they are bonded? If they are not bonded, when you are applying load, so suppose if you take two particles, they are coming together and they touch each other. Now, if you want to separate them, there will be no resistance offered by these particles to be separated, but imagine they are bonded. When they are bonded, then you need to overcome that bonding force, and then only they can be separated. So, that means you have to talk about what is this tensile force that you need to apply in order to separate them. There are other parameters like, are you doing the simulation on earth or in space, right? The results will matter, because the gravity plays a role, and hence the load that is experienced, the forces experienced by the particles at the bottom of the container will be different from the ones that are at the top. So, take the example of a silo. So, the bottom particles are experiencing much larger forces, because the top particle, all the weight is transferred through the particle contacts. And what is the porosity? So, that means, what do I mean by porosity? How the particles are packed, right? Is the entire container completely filled with no voids, or there are voids in the container, and that matters because that restrains or enables particle motion depending upon the amount of porosity or the gap available. And this is an output parameter which is called a coordination number. So, you look at any particle in the assembly, how this particle is connected to its neighbors, how many neighbors does the particle have. When I say neighbors, how many contacts does this particle have, because that is an important parameter in for us to understand the macroscopic response of the system. So, these are all the ingredients in a DEM setup, where you input most of these parameters, and you actually can, as a part of the solution, you can calculate this contact radius, which will decide what will be the motion, and this coordination number is one of the important parameter that allows us to understand how the packing is there in the system. Yes.
Coordination number, can you?
Yeah. So, let us say you are sitting there. So, you have one person to your right, one person to your left, one person behind you. There is nobody ahead of you. Okay. Let us imagine you are only looking at left, right, forward, backward. So, your coordination number now is 3, because you are surrounded by 3 neighbors. Okay. So, now let us take him. So, his coordination number is 1, 2, his number is also 3, his coordination number is also 3. Interestingly, nobody has a coordination number of 4 in this class. Huh? Yeah, you sat in such a way that you do not have a coordination number of 4, right. But what do I mean by that is how many nearest neighbors you have. So, if you have a particle, so let us see this example. So, let us say this is the particle that I am paying attention to. This particle is surrounded by I am looking in the assembly. Okay. Now, what is the coordination number of this particle? So, this particle is in contact with this fellow 1, this fellow 2, this fellow 3, that fellow 4, that fellow 5. So, as far as DM simulations are concerned, your coordination number of a particle is the number of nearest neighboring contact particles that it has. So, for example, this fellow is close by, but it is not touching, and hence it is not participating in the contact interaction. So, for this fellow the coordination number is 5. Now, let us look at this fellow. For this guy the coordination number is 1, 2, 3, and for this guy 0, right, and for this guy 1. So, each particle in the system has a different coordination number.
But this will change in the next instance.
Exactly. So, imagine a scenario wherein, let us say you are sitting in this room right now, and each one of you have a comfortable coordination number. Okay. Let us say I open the door and I let people in, and I am not stopping the number of people coming in. As people start coming in, you will be rubbing your shoulders with others. That means, number of people that you are coming in contact with is increasing as a function of time, is not it? That means, the coordination number of individual particles is increasing, and as a result the coordination number of the average coordination number of the assembly is also increasing. So, if an average coordination number of an assembly increases, what is the meaning of that? There is more packing in the system. So, that is why the coordination number is a measure of state of packing in your system. Okay?
So, it's an input to the simulation or
No, it is not an input. It is what you, it is a state variable in some sense. You actually can find out at each and every instance what is the coordination number, because that sort of represents the state of packing in a, yeah, because you are actually talking about, so there is the silo is confined by your container, right, and these particles are transferring forces, and each particle, the force is distributed by, is collectively taken by particles, and a lot amount of force is dissipated in the frictional, the tangential force, right. So, each particle effectively may not be experiencing the crushing force, but collectively they are supporting that load. That is why you do not see particle breakage. Otherwise, in silos what should happen is at the bottom all your particles should be breaking. Sometimes you will see that, for example, if you are transporting vegetables, like for example, you transport tomatoes, right. So, if you pack them, typically the bottom most tomatoes are little bit more crushed compared to topmost ones, right. That is precisely what you are expecting. In silos what happens is, there will be an arch formation that takes place, the force distribution is such that individual particle is not experiencing that force. You will not be able to see if you are doing that unless you have a mechanism to represent this arching behavior. So, that is where the macroscopic constitutive response is changing, right. It is not the same as individual particle. So, in the continuum mechanics perspective, if you are applying that load, so then locally at the bottommost one, if you are applying gravity through that, then this is basically due to gravity, right. All that, so the body load is changing as a function of position, and that force has to be transferred, and in continuum mechanics you have to incorporate such a constitutive response to the granular system as when you are modeling it as a continuum. Otherwise, you may not be capturing the right physics. Okay. All right. So, I hope the concept of coordination number is clear. So, that is why you need to do simulations, right. So, you do the simulation, and in the experiment what is that you can measure? For example, if you take a box of container full of balls and you are applying force, what is that you can measure? You can only measure force displacement response, and you do a DM simulation and get the force displacement response, if your post displacement response obtained from the DEM simulation matches with the experimental data, provided you have taken all the properties correct, then you have some hope that okay, because my macroscopic response is matching, now whatever is happening internally makes sense. What one point that we always should keep in mind when we are doing DEM simulations, it is really a nice tool for deciphering qualitative information at the micro scale by actually comparing the macroscopic information. But if you really want to have a quantitative values, it may not be accurate, because you may not have a unique solution. A different combinations of microscopic interaction may give you the same macroscopic interaction, but the hope is that you somehow ensure that by changing certain, so suppose instead of doing one simulation under one boundary condition, you do under couple of boundary conditions and corresponding experiments. In all the cases, if the experimental data and modeling data matches, then you have a confidence that okay, everything seems to be matching, and hence my microscopic information I can have a quantitative comparison also. So, this is something that we have to be very careful when we are doing this simulation. Okay? All right. So, again it allows us to interact. So, what are the other aspects of DEM is that something that is very important in a DEM simulation is collision detection, meaning when two particles are moving. So, imagine all of you are running, I am trying to simulate that running process by giving each one of you a velocity, right. So, will I be able to predict when you guys collide with each other? In this room, imagine all the tables are removed, and now I have given some initial velocity to all of you. That means I have given the direction as well, right. And then I observe, and I should be able to find when you are colliding with each other. If two people are colliding with each other, what happens? Your velocities will come down, or you will change the course, or you may stop. So, that means if I have to simulate that process, imagine I should be able to detect collision first, whether there is a collision that is happening or not. That means a contact detection has to be done, right. So, again the other aspects I will talk about later, the other points, but important, one of the important aspects in a DEM simulation is the ability to identify the contact of a particle with its neighbors. So, here I am describing a simple flow chart of a typical DEM simulation. Okay. So, how do I go about doing a typical DEM simulation? You have a granular assembly with defined initial positions. That means you know what are the positions of your particles, what is your domain, okay, and you have initial velocities and initial orientations. Here, because all of them, let us say all of them are spherical particles, then I do not need to worry about orientation, isn't it? If it is non-spherical, then I have to say in which direction the particle is oriented. So, initialization of the system is the first step. That means I need to specify what are the positions of all the particles. If it is a spherical particle, all that I need to specify is what? The center of the particle, right, each particle, and the radius. If it is a uniform radius, you say all the particles are having same radius. If it is not, then you have to specify the radius too. And then their velocities, what is their initial velocity? They may be at rest. So, initially all of them have 0 velocity, but they may be moving too. Then what is the initial velocity? And then you take that structure, right. So, let us say I have this container, so let us say these are the particles, and I am going to do a compression experiment. I always take compression experiment because that is something that is easy to comprehend. You have a piston and you are trying to compress. This is the initial configuration of the system. So, when I say I have to define my boundary, my domain is This is my domain. That means none of my particles are outside, and hence whenever I am doing the calculation search, I need not search outside this domain, isn't it? I only am limiting my search within this domain. And now initially I have defined these particles, so I know what is the position and radius of all these particles. So are there any contacts right now? So you say that particle, so let us say this is particle 1, 2, 3, 4, 5, 6, 7. So you say that particle 3 is in contact with wall, particle 6 is in contact with 7, particle 7 is in contact with wall, right, and no other particles are having any contact, right, depending upon the distance between these particles. So let us say you have a particle here and you have another particle there. So there is some overlap that happens, right. Physically this overlap does not happen, but what is the meaning of that? This is a mathematical construct. So you have one particle and there is a wall here, but the particle is just not touching but actually pushing the wall, because of which if you look locally, it may be because of your packing, this particle is not perfectly spherical. If you look at locally, the particle might have done this to set up. Okay. So imagine this, because we do not actually model individual particle deformation in DEM, we consider the particle to be deformable, but we do not model the deformation. Okay. So this is the particle, so this is what I call a overlap, right. So depending upon the amount of overlap, I define what is the force between these particles, right. So calculate the force and torque on each particle. It may be that, or initially let us imagine that there is no force acting there is no contact force acting on the particles, but let us say you are applying this force at time t equal to 0, you have applied a force of 1 Newton. That means this particular particle is subjected to a 1 Newton force, correct. Because it is subjected to 1 Newton force, then we need to understand the dynamics of that particle. So all that you need to calculate the forces. Once you have the force, if you know the force acting on a particle and you know the mass of the particle, we can calculate the acceleration of the particle, isn't it? This is Newton's second law of motion. So what you do is, in this configuration you have frozen, imagine this configuration is frozen in your mind, okay, and at that frozen configuration you find out what are all the forces acting on the particles. Suppose this system is under gravity, then gravitational force will be there or not? On each particle it will be there. So every particle is subjected to some gravitational force, first thing. And the second thing is, the particles may be touching each other, because of which there may be contact forces. So on each and every particle, first of all you need to see how the contact interactions between the particles. That means you need to do the contact detection. After doing the contact detection, you need to calculate the contact forces. Now you need to set up for each particle what is the total force acting on the particle. So if you have 1000 particles, you have 1000 forces, each one of them is subjected to that force. And now for each particle you solve this equation, F equal to ma, and then what you will get? You will get acceleration. And if you integrate acceleration, what will you get? If you integrate acceleration, velocity. If you integrate velocity, displacement. But when you are integrating, you have to do this over a very small time step, so that you know within that small time step with that acceleration where is the particle moving to the next step. Why do we need to do it very small time step? Why do we need to do it with very small time step? If we do not do with very small time step, let us say, what is acceleration? Roughly speaking, dv by dt, right. So by integrating this I can get velocity, right. So that means velocity is equal to integral t to t plus 1 a dt, that is what I am trying to do, or t plus delta t. So what is that I am getting here? I am getting the velocity at time t plus delta t. Let us say if this time t plus delta t is so high, and then you will calculate the displacement, that is integral v dt at time t to t plus delta t, correct. So, if my time is very high, that this particle, we are doing it for each particle and we are only calculating the force. But in reality what is happening, this particle is in contact with this fellow. If you take a very large time step, what will happen is this particle may move here in your simulation without actually accounting for the fact that this particle is sitting there. So, your delta t that you are choosing should be sufficiently small, so that the particle's neighbors are not changed immediately. It should not be changing immediately at a short notice, right. It should allow these particles to interact, and so that you are not losing on the dynamics happening in the system. So, that is the reason why you need to have extremely small time step. Okay. After doing this calculation, so integrate equations of motion to calculate the new positions and velocities. So, what we are doing is, so these particles positions are such that they move, and now you look at the, you do not all that you will do is you will actually monitor the position of the center of the particle if it is a spherical particle, and you realize that these two centers are so close that there is an overlap between the particles. Because of the overlap, there will be a contact force generated between the particles, and that contact force will push them apart. The reason why we are creating a contact force is because normally it will not allow these forces, right. So, that contact force, there will be a resistance to this interpenetration, unless this force is much larger than these contact interactions, these will continue, otherwise they can separate out. So, you are calculating what is that force that has to be. So, if your two particles are interacting, there is a reaction force that is generated that will separate them out, right. And if you have another force that is coming this way, which is not letting them separate, then they will continue. But if, so you imagine this scenario, if you are applying force, what happens? If you are trying to push both of them, what will happen? Push them, do that experiment, do it harder. What is happening? Contact force is increasing, right, your resistance is increasing. So, your constitutive relation will be such that when the overlap is increasing, that means you are trying to come together, there will be a the resistance force that increases significantly to avoid these particles passing through each other. It will never let it do. So, we will see what kind of constitutive relations do that. For example, Hertzsch-Mendelian contact law. So, that is why contact constitutive relation is very important, how it enables that. Here I am explaining the algorithm right now, but there are two approaches for DEM simulations that we will talk about. Whatever I am talking about right now is something called a soft sphere approach, wherein the particles are considered deformable, but we will not model the deformation. Okay? It's depends on the contact constitutive response. You should not allow significantly high amount of overlap, right? It should be a fraction of your, a smaller fraction of your radius of the particle to be realistic, right. So, depending upon the contact constitutive relation, that means you have to add higher penalty, so that you minimize the interpenetration. So, that means if you are pushing, so imagine you are applying a force from this side, when these particles are pushing each other, then what happens? This force is increasing significantly. When this force increases significantly, this force is constant, and hence this is able to push it apart. Okay? And then you calculate the positions, new positions, and accumulate the statistics to calculate transport properties. What do I mean by that? Basically identifying what is the macroscopic stress, what is the macroscopic strain, what is the coordination number at that particular instance, what is the packing fraction at that particular instance, what is the fabric at that particular instance. Yesterday Professor Zhao talked about fabric, right. We will see what do we mean by fabric, how do we go about defining it, right. So, that means it tells you about the overall anisotropy of the system. Is the anisotropy of the system changing? So, these are all the properties that you can get access to by looking at each and every particle. and then you have done that for that time step, then you go to the next time step. So, in that configuration you again calculate. So, you have moved all the particles, you have taken initial system, and now if you take this system, what would have happened? This particle would have come down, and this particle would have come here, and this particle would have come here. I am talking about these 5 particles, right. Now, this is the new configuration. In this new configuration, again your contact network has completely changed, isn't it? Earlier the particles which were not in contact are not now coming in contact with each other. So, now you need to re-establish the contact connectivity and then calculate based on the interpenetration, because the positions are now changed. On this new interpenetration you calculate new contact force, again solve for this. You do that until the time that you want to do the simulation, right, and keep updating. So, at its core, what the DEM is doing is solving Newton's second law of motion, as simple as that. A very simple equation we are solving, and of course, here I have written 2 equations, F equal to ma and T equal to I alpha. This is, what is this? This is conservation of what momentum? Linear momentum, and this is angular momentum. And you are talking about, say for example, if the particles are subjected to torque, so then you have angular acceleration, and this is what I is your mass moment of inertia. So, the angular acceleration has to be captured. So, you can capture both linear as well as angular accelerations, velocities and displacements, and is extremely important to be able to capture these things particularly when you are dealing with non-spherical particles, right. Then when you are compressing is, are there some particles which are actually having local rotations, right. All these things can be captured. I will talk about it, they are coming. This without collision, how will the contact take place? If they are not colliding, they are not, how will the contact take place? So, I will come there. What you are referring to, you are talking about a hard sphere approach, we will talk about it. So, now there are 2 main variants of DEM simulation. One is a hard sphere model, another one is soft sphere model. All that we were talking till now was a soft sphere approach. Now, let us look at hard sphere model. It is also called, these are also called event driven models or collision models. What it does is, it does not account, it does not let the contact have any interpenetration. These are all hard spheres, there is no deformation whatsoever possible, right. They simply look at the event. So, whether there is a collision between 2 particles. So, you probably have done this in your high school, wherein you suppose if you take a ball, if you drop it, right, you can calculate what is the height to which it comes, depending on what? Will it come back to the same height? No, it will not come back to the same height, it will come back to some height, right. What will be that height? It depends on what? What property? There is something called coefficient of restitution, right. When coefficient of restitution is 1, then what happens? That means, it means that there is no dissipation. So, the dissipation mechanism is embedded in your coefficient of restitution of the material, right. So, the coefficient of restitution is a property of what? It is not the property of the particle, it is the property of 2 contacting particles, right. You cannot have a coefficient of restitution for steel, you will have coefficient of restitution for steel on steel, steel on wood, steel on soil, steel on concrete. It is a contact property, right. You should know what are the materials that you are simulating, and in the assembly if you have 2 or 3 different kinds of materials, you should know what is the coefficient of restitution between each class of materials, right. That is the dissipator, energy dissipator, right. So, what it does is it simply solves momentum exchange. E change is not correct, it should have been exchange. So, sigma mv is equal to constant, right. That is what it does, and it does not account for interpenetration, as I told you, and there is no deformation during collision. There will be collision, but there is no deformation. The moment they touch, V1, V2, two particles having mass m1, m2, right. So, they touch and then they come back depending upon the direction of your velocities. And so, the loss of momentum is solely characterized by this property called coefficient of restitution. So, you will have different values for normal and tangential coefficients of restitution. That means, you have, suppose if the particles are coming head on collision, what about if they are colliding like that? So, this particle is going this way and this particle is coming this way and they are doing this kind of interaction. That is also a contact interaction. So, the coefficient of restitution in this case may be different from this case, right. You can specify that, and this is typically used for rapid granular flows such as avalanches, because otherwise calculating contact force and ensuring the non-linearity of these contact force interactions and all takes lot of time. So, when you are not interested in what is happening to the deformation of individual particles, it is not recommended to use your soft sphere approach, particularly for large scale granular flows such as avalanches and manufacturing processes. Probably we can resort to hard sphere model, which is simply considering momentum exchange. So, this is the cartoon of this hard sphere model. You have this m1 and m2. So, two particles before contact, they are moving with velocity v1, v2, and when they touch each other, so the contact duration in this case is 0. That means, the touch and they separate out, they will not be staying together, okay. And there is no overlap whatsoever. After post contact, you will have v1 dash and v2 dash depending upon which direction they are moving. So, this is the basically it depends on this v dash or v1 dash or v2 dash depend on the change in momentum, which is which also depends on the coefficient of normal restitution, coefficient of friction, coefficient of tangential restitution, because there is dissipation through friction too. So, all these things will define how this v1 dash changes, right. So, in the event driven problems like hard sphere model, one of the most important differences compared to a soft sphere model is that a particle at a particular instance will be in touch with only one other particle. It will not have simultaneous interactions at the same time. You will solve for one particle will be in contact with another particle, only one another particle, and then it will contact the other one, because otherwise you will not be able to solve for this momentum exchange, right. So, that is why your contact detection is little simpler compared to the other one. Now, coming to the soft sphere model, here what we do is we solve equations governing both linear and angular dynamic equilibrium, right. Here please keep in mind that soft is a misnomer. Soft does not mean that we are accounting for shape change of the particle. We do not account for shape change of the particle. The particles remain spherical and of the same size, they do not change their shape, yes. So, you have to have very small delta t. So, this particle comes in contact with this fellow and exchanges momentum and goes and hits another particle, right. You should have extremely small time step when you are dealing with event driven approaches, but because the contact detection and contact constitutive relation calculation is very small, the overall time will be less for large scale. For example, the way that you initially, how will you have the initial configuration? You have to generate the particle systems, right? When you are generating the particle system, so let us imagine a scenario of dropping particles in a container. What happens when you drop the first particle? It will be bouncing, right? Drop the second particle. In this process, it will whichever particle it hits the first. You may have a scenario where a particle is hitting two particles at the same time. Yeah. So that is your concern. What will happen? You then your algorithm should choose which one to do first. That's all. Okay. So maybe you can say that okay, this guy has first. So your algorithm should have some mechanism to deal with one of those particles. But at a time, the momentum exchange cannot happen between one and another three particles. It can happen only with one more particle. So another model, the second model, is what we mostly use for slow granular motions, right, where particles are not having large scale deformations or the motion is not significant. That is your soft sphere model. Again, as I said, the soft is a misnomer, because we really don't, the particles are not soft in the sense that they can be compressed to a very large extent. The particles remain as they are. We do not simulate the deformation of the particle, but we allow for interparticle overlap, and based on the overlap we compute. So, the particles are rigid, but they can overlap at contact points, and this normal contact force depends on the extent of overlap or the particle separation distance, depending on whether there is cohesion between the particles. Similarly, you can also have shear and tangential interactions, and this allows us to deal with multiple contacts simultaneously, because you are having a finite amount of time of interaction. So, the particles, you can calculate what is the interaction of the particles on one particle due to other particles, and then calculate the total force, effective force acting on that particle, that decides what will be its next position. So, this is the soft sphere model is based on the distinct element method proposed by Kondal and Strack in 1979. So, this is very similar to whatever we are talking today as a discrete element method. Right? There are other methods, there is discontinuous deformation analysis method, and we are not going to discuss these techniques here. So, this is how the cartoon of a soft sphere model looks like. So, you have particle M1, M2. Earlier, your contact duration was 0, right? They are not sitting in contact forever, they touch and leave. Here you have contact duration is greater than 0, and you have overlap. Earlier there was no overlap, and based on the overlap you calculate your next velocities, because you will calculate the force, from there you calculate acceleration, and you calculate based on the overlap you calculate the contact forces using a contact constitutive model and the inertia of the particle. Okay. All right. So, let us look at this. Let us say you have, as I said, it is a numerical method, a family of numerical methods for completing motion of a large granular system. So, you see here some ceramic pebbles which are put in a container. So, if you say you have a system like that, now let us zoom in to any two particles. So, you see that this is particle I and this is particle j, and particle I has a radius of r and particle j also has a radius, another radius r, and when, because these two particles are centers are so close that you have some contact overlap, that is, this A is what we call contact area. Depending on the contact area, we will calculate what will be the contact force. Okay. It is very similar to having, so you take two particles and imagine having a spring between them, a nonlinear spring, and then when you are compressing, depending upon the stiffness of the spring, you will generate some force. That stiffness depends on the overlap of the particles. So, you can calculate the total force acting on each particle. So, let us say particle I, you can calculate the total force acting. It can be coming from different routes, I will talk about that, and divided by the mass will give you the acceleration of particle I. Similarly, total moment acting on the particle I divided by the moment of inertia, mass moment of inertia will give you angular acceleration experienced by the particle I. At every instance, for each particle at every time step, if you have 1000 particles, you have to do 1000 such computations. Okay? And the interactions, particularly in this case, you can have an elastic contact, meaning there is no plasticity. So, we assume that the particles are not undergoing plastic deformation. And there is of course a frictional force, which is the dissipative part of this contact in general, but you can also add other forces like plastic deformation you can include. You can also include something called a viscous force, an adhesive contact, several other things can be added to this sigma Fi. So, this sigma Fi can have all sorts of forces either coming through the contact interaction or from the external sources. Is that clear? Is this concept clear? You are talking about overlap, and if you imagine two spheres are overlapping and they will create a circle, right. The radius of that circle is what we call contact radius, okay, and that depends on the extent of overlap. Yeah. It depends on the mass, no, mass and moment of inertia of that particle. The forces are same because it has to be in equilibrium, but the masses will be different. And also u may be same, but then your velocities may be different because the previous velocity direction may be different for particle I and particle j. Alright, a contact pair means two particles coming in contact. In a particular scenario, you may have a particle in contact with more than one particle. This is contact pair 1, this is contact pair 2, contact pair 3. So, when I say sigma Fi on the particle, so now if I take this particle, on this particle I have force coming from this contact pair 1, force coming from contact pair 2 and force coming from contact pair 3. Agreed? So, let us say let us not worry about the moment first right now, and this is the, now you can calculate the net force acting on the particle, you can resolve the forces vectorially and then you can solve this vectorial equation. So, the net force acting on the particle you have, from that you will be able to calculate what is the acceleration of the particle vectorially, that means all the three components of the acceleration. Similarly, all the three components of the angular acceleration. So, let us say you have a, here I am showing you a binary pebble assembly. Can you see that? There are two different sizes. This is one size, this is another size. Do not worry about the color coding is of something else. And if you look at any two particles, so this is particle I and particle j, and if there is contact between them, there are, so delta ij is the particle overlap, that is close to approximately equal to Rs plus Rg, which means they are just touching, isn't it? If delta, the distance between them, not overlap, the distance between them is just they are touching. And now, if the distance, actual distance between centers is smaller than this Rs plus Rg, then you know that there is a overlap, correct? Yes or no? Now, depending upon the overlap, I told you that there is a contact constitutive relation which depends on the overlap, and that will give you the values of F1 and Ft. So, imagine you are a just to compute that force between the two particles. So, you know that they cannot interpenetrate, right, but numerically we can allow them to interpenetrate, and that amount of interpenetration allows you to compute what is the force acting. So, imagine a spring between the particles and you are pushing, the stiffness of that spring offers resistance, isn't it? How do you know the stiffness of the spring? Depending on these two materials properties and amount of apparent overlap, not the real overlap, and that stiffness depends, is what is given by the contact constitutive response. Okay? I will show you the equation, then it becomes clear. Okay? So, now you have a normal, imagine two particles with a normal spring and a tangential spring. Normal spring talks about normal interaction, tangential spring talks about tangential interaction between the two particles. Is that clear? So, from that you can calculate force, contact force between particle I and j, which is normal force and tangential force. So, now if you have a macroscopic assembly, such a single size particle assembly, right, and you are doing some compression of this assembly, uniaxial compression, right, then you can compute the macroscopic stress and macroscopic strain. All that you are doing is you are only compressing. So, since you are compressing, let us say it is a displacement controlled experiment, that means you are pushing the piston, then you can calculate strain. Can you or can you not? Because you know the initial size of the assembly, and by moving the piston you know the displacement by the initial size is your strain. In each direction you can compute. So, you can actually compute the strain tensor, not only a strain component in a particular direction, right. So, now you know what are the contact forces acting on the each and every particle, right, in the entire assembly. So, at each and every instance of time you can compute what is the macroscopic stress in the assembly, and that is given by this equation. This is what we call a volume average stress. At each and every instance you know what is my overlap and what is my contact force. Similarly, this is what is my normal contact force and shear contact force. Based on these values and the direction of the normal and the tangent, you can compute each and every component of the stress tensor. This is what we call a volume average stress tensor, which essentially depends on normal force and I and j, I less than j for all the particles. So, you have to do this for all the particles with between I and j, they go from I1 to number of particles. So, first between first particle and second particle, first particle, third particle. So, you have a structure, right. Let us say you have 10 particles in the system. So, let me show you what happens. Particle 1, particle 2, particle 3, particle 4 up to 10 particles. Particle 1 at this particular time instance t is equal to t naught, we are computing. Particle 1 is having a contact with 2 and 10. 2 is having, because the fact that particle 1 has contact with 2, 2 should also have contact with 1, right, but there is no point in writing it because it is already done. So, we will not write. So, let us say it has contact with 8 and 6, and 3 has 4 and 7, 4 has 5 and 1, like that. I am only writing 2 contacts, you may have more contacts. Now, what you can do is, we will go from each and every particle. First look at first particle, what is the contact force between first particle, second particle, first particle, 10th particle, and their normal between the first and 10th particle will be different, first and second particle will be different. So, you do for each and every particle and then sum over all the particles in the assembly and divided that with the volume of the assembly, then you will get the macroscopic stress. This is one way of computing macroscopic stress. There is another way. You are applying force, the displacement. So, this wall through which you are applying the displacement will experience some reaction force, isn't it? Yes or no? So, that reaction force divided by the area is also a macroscopic stress, isn't it? If you are interested in that stress quantity. This is what we call the computation of macroscopic stress using the microscopic information, because we are looking at the contact force at each and every particle contact pair. From that we are deducing the macroscopic stress, but it should be equal to whatever is experienced by the wall. We are compressing from the top wall. So, they should be the same. That is how you verify whether your code is correct or not. So, this is one simple example where what we are doing is we have a granular assembly like this and you are compressing, and you see you have computed stress the way that I have shown as a function of strain. You are loading and then you are unloading. That means you have compressed and decompressed. You are compressing the system and unloading the system. These two are interesting images you can see that as you are compressing, the potential energy, that means the energy stored in the particles, because they are subjected to some deformation, right. Although we are not modeling the deformation, there is some strain energy stored in the particles. So, this is what we call potential energy that increases as the compression takes place. And here at the bottom left corner, we are showing force chains. What do we mean by that? So, you have a particle, this particle is in contact with this fellows. Now, this particular geometry can be represented by something called force chains. So, you can show this geometry like that. Centers of the particles are connected and the magnitude of this line represents the amount of contact force between the particles, and it is a very nice way of representing what is happening in the system. And you can clearly see some of the contacts or some of the chains are thicker and some of the chains are thinner, and then you will be able to see where is the localization taking place. Suppose if there is a force localization taking place, you will be able to see through this force network system, right. So, this is a simple uniaxial compression experiment. You can see the particles are elastic particles, there is no nonlinearity in them. So, all mechanical property of this particle is E, which is elastic. Although the constitutive relation for the particle is elastic, you see that the macroscopic response is nonlinear. That is what I was mentioning, right. Okay, I think we will stop here, and there is a lot to discuss that we will do in the next class. Although, so you understood the basic algorithm of discrete element method, right. So, we are actually looking at each and every particle, identifying what is the force experienced by each and every particle, and then that force will be used to compute the acceleration and integrate acceleration to get the velocity and positions. The calculation of this force that is acting on each particle can be done in different ways. That means the position update. If you take hard sphere model, then there is no interpenetration, then you will simply use exchange of momentum, right, and then calculate the positions of the particles. If you are using soft sphere model, you actually use the apparent overlap between the particles in order to compute the force acting on the particle, and that force is used to solve your Newton's second law of motion, and then get both linear and angular displacements and velocities and accelerations. So, that is the crux of your DEM simulation. Now, the force that we are talking about is only contact force that we have talked about, but if imagine this particle while being in contact is in a fluid medium, then what is the other force that this particle can experience? The drag force offered by the fluid. So, that will be another force acting on the particle. Imagine this particle is sitting in an electrostatic field, right. So, then may be electrical forces acting, and imagine this particle sitting in a magnetic field. So, the magnetic field forces may be acting, and this particle sitting in under certain gravitational field. So, body force through gravitational field will act, and in addition to that you can apply an external force, and an external force is usually applied to particles on the boundary, and all those forces are transferred through the contact points to other particles. So, only you apply forces on the boundary, but other particles experience that through the contact forces, right. So, this is the crux of the basic algorithm, and using that we do various simulations, and the only change, the complexity increases depending upon what kind of constitutive relation that you are using in order to prescribe a force corresponding to certain overlap, right. If you want to add additional complexities, you need to make that contact constitutive relation to be different. Other than that, the basic algorithm remains the same, okay.